World War II had already shown the world the destructive power of aircraft, but nothing compared to the promise of the B-29 Superfortress. On paper it was a technological marvel, a bomber faster and higher than anything the Japanese could reach, carrying heavier loads and armed with more defensive firepower than previous bombers. At a staggering $3 billion investment, it was the most expensive weapon the United States had ever built, more than the cost of the atomic bomb itself. It was intended to dominate the skies over Japan, to crush the enemy with precision bombing that could shorten the war. Yet before it could prove its worth in battle, the B-29 was already destroying itself. The problem wasn't enemy fire, nor were flak guns the cause of its greatest threat. It wasn't poor strategy or inexperienced crews. It was the plane's own heart, the Wright R-3350 duplex Cyclone engines. Each engine, a mechanical giant with 18 cylinders producing over 2,200 horsepower, was supposed to push the bomber to speeds of 350 miles per hour at 30,000 feet. In theory it was perfect. In reality it was a ticking time bomb. The main issue was heat, particularly in the rear cylinders of the engine. Each R-3350 had 2 rows of 9 cylinders. The front row faced the incoming air, which rushed through at roughly 200 miles per hour, keeping the cylinders within safe temperature limits. But the rear row sat in the shadow of the front, barely exposed to cooling airflow. The temperatures in those back cylinders climbed to 550 degrees Fahrenheit during standard operations and could spike above 650 degrees during takeoff or climb. Aluminum cylinder heads, critical to the engine's operation, began to warp at around 500 degrees. Exhaust valves failed at 575 degrees. And if the temperature hit 600 degrees, a catastrophic seizure could occur. Pistons would stop moving while the crankshaft continued spinning at 2,800 revolutions per minute. The result was devastating. Connecting rods snapped like sticks, pistons punched through the cylinder walls, and hot oil sprayed across burning metal. In the worst-case scenario, the magnesium alloy engine casing ignited, producing flames hotter than 5,600 degrees Fahrenheit, enough to melt through the main wing spar in under 2 minutes. Fire suppression systems on the B-29 were powerless. The flames were internal, unreachable. Boeing and Wright Aeronautical, the companies responsible for the bomber and its engines, tried every conceivable solution. Larger oil coolers were installed. Adjustable cowl flaps were redesigned to force more airflow. Engineers enlarged air intakes to increase ram air to the engine. Each fix seemed promising but introduced new complications. Bigger cowl flaps caused aerodynamic drag that prevented pilots from fully opening them during critical phases of flight. Adjustments that should have worked often created equally dangerous side effects. Despite months of effort and millions of dollars invested, the engines kept failing. By the time combat missions began in June 1944, the problem was no longer theoretical. The B-29 was already claiming its own victims. Statistics from the early Pacific operations revealed a grim reality. Out of 414 B-29s lost in the war, only 147 were shot down by enemy action. The remaining 267, nearly 2/3, were destroyed due to engine fires, mechanical failures, or mid-air explosions caused by their own power plants. Pilots began referring to the aircraft with a grim nickname, the Flying Funeral. Crews requested transfers to older bombers like the B-17 and B-24, even though those planes were slower, carried smaller payloads, and lacked the advanced defensive armament of the B-29. Fear of being incinerated by your own engines surpassed fear of enemy fighters. The situation had become desperate, and the American military was losing planes faster than Boeing could produce them. In June 1944, the National Advisory Committee for Aeronautics, NACA, the organization that would later become NASA, brought a B-29 to their Cleveland laboratory to study the engine failures in controlled conditions. The plane's engines were run in altitude wind tunnels, simulating the high-altitude conditions of combat. Dozens of sensors were installed, measuring temperature, airflow, and pressure at multiple points across each engine. The engineers confirmed what everyone already feared: the rear cylinders were dangerously undercooled. Yet the experts were unanimous in one conclusion: there was no feasible solution without a complete redesign of the engine. The R-3350's power-to-size ratio was too high, the thermodynamics too unforgiving. Any attempt to push more air through the engine would compromise structural integrity, efficiency, or safety. Unsolvable was the word being whispered in engineering labs. The B-29 program, the crown jewel of American aviation, seemed on the brink of disaster before it had even truly begun its combat mission. Amid this technical stalemate, while engineers pored over graphs, airflow calculations and wind tunnel results, the solution would come from an entirely unexpected source. It wouldn't be a PhD aeronautical engineer or a scientist at NASA. It wouldn't be someone who had spent years developing aircraft engines. It would come from a 38-year-old plumber from Cleveland. While the world's best engineers wrestled with the impossible, Tony Valader was quietly about to change the course of the war. Born in 1906 in Cleveland's Little Italy, Tony grew up in a family of immigrants who scraped by through hard work. School was a luxury he couldn't afford. By age 14, he left classes behind to help his father in the small plumbing business. He learned quickly that water, like life, followed the path of least resistance. If water wouldn't reach a radiator, he didn't just pump harder. He redirected it, created bypasses, guided the flow. By the time he was 20, Tony was one of Cleveland's finest troubleshooters, able to solve problems that baffled others. When the United States entered the war, Tony was 35, too old to fight, but the war needed minds as much as it needed bodies. He applied to Curtiss-Wright, hoping his skills with pipes and pressure might translate into aircraft work. Curtiss-Wright assigned him to Pratt Army Airfield in Kansas, where he performed maintenance on the notorious R-3350 engines. He had never touched a 2,200 horsepower aircraft engine before. A 3-week training course was all he got. Yet in Tony's eyes, the principles weren't so different. Fluid, whether water or air, behaves predictably if you understand its path. By September 1944, the B-29 program was in crisis. Engines were failing during takeoff, engines were exploding on runways, and crews were terrified. Training flights had to be canceled. Standard solutions had failed. Cowl flaps, larger air intakes, redesigned oil coolers, all ineffective. Wright Aeronautical's top engineers had torn engines apart, redesigned baffles, and confirmed through calculations that rear cylinders were dangerously undercooled. But the problem remained fundamentally unsolvable. Tony's first hands-on encounter with a failing engine changed everything. Assigned to inspect engine number 3 of a B-29 that had overheated during a training flight, he removed the cowling and stared at the rear cylinders. Blackened and warped, they were screaming under temperatures no material should survive. He traced the supposed airflow path. The intake sent air over the front cylinders, then through narrow channels to the rear. But in reality the air barely moved. Heat from the front row stagnated in the back, actually increasing temperatures instead of cooling them. Tony recognized the problem instantly, not as an aeronautical engineer but as a plumber. He remembered a building he had worked on years ago, where radiators on the 3rd floor never received enough hot water. The problem wasn't the pump. It was the path. The water always chose the easy route, bypassing the floor that needed it. His solution had been a small bypass pipe, redirecting some of the flow to the neglected area. Simple, elegant, and effective. As Tony looked at the engine, a similar idea formed. If the airflow couldn't reach the rear cylinders naturally, why not create a new path? Why not guide the air directly where it was needed, instead of relying on complex, chaotic channels? He sketched diagrams on a maintenance log, imagining small aluminum ducts that could divert air around the front cylinders and blast it onto the rear. It was almost laughably simple. Yet he knew the engineers would hate it. Without asking for permission, Tony spent 3 nights crafting a prototype. He scavenged aluminum tubing from damaged B-29s, borrowed tools from the hangar, and modified cylinder baffles. The ducts were crude, hand-formed, attached with sheet metal screws and high-temperature sealant. They looked like a plumber's experiment, not a solution for a multimillion-dollar aircraft. But the principle was solid. Direct the flow to where it was needed, regardless of the complicated design the engineers had created. By October 3, 1944, the modification was complete. Tony didn't tell his sergeant, the engineering officer, or anyone in authority. He simply signed off on the maintenance record. Inspection complete, engine cleared. The next morning, Captain James Wheeler ran the engine as part of routine testing. Normally, the rear cylinders would hit 550 degrees Fahrenheit within a minute and a half. Instead, the temperature stabilized at 425 degrees, cooler than the front cylinders. Wheeler assumed the gauge was broken, ran the engine at full power for 5 minutes and could not believe what he saw. Tony's solution, born from years of working with pipes in Cleveland basements, had tamed one of the deadliest engines in history. Without advanced equations or wind tunnels, without 20 months of government research or millions of dollars in experimentation, a plumber had solved what aeronautical science could not. Word of Tony Valader's overnight modification spread quickly through the hangar, though no one officially approved it. At first, the other mechanics were skeptical. A plumber fixing one of the deadliest engines in existence? Surely this was a joke. Yet the data didn't lie. Engine number 3, with its hand-formed aluminum ducts, ran at 425 degrees in the rear cylinders instead of the usual 550. The difference was undeniable. Still, in the military hierarchy, evidence meant little without formal approval. Tony's superiors were concerned. Unauthorized modifications on a $4 million aircraft were a serious offense, potentially sabotage in wartime. Major Donald Peterson, chief of aircraft maintenance at Pratt Army Airfield, summoned Tony to explain himself. The mechanic walked into the office, grease-stained and exhausted, carrying only the maintenance log where he had sketched his duct system. "Sergeant Valader," Peterson said, his voice clipped, "you modified a combat aircraft engine without authorization. Do you understand the severity?" "Yes, sir," Tony replied calmly. "But the engine ran cooler. The rear cylinders stayed safe." Peterson's eyes narrowed. "You know this could be court-martialed?" "Yes, sir," Tony said again. "But it works." Peterson reviewed the temperature readings from Captain Wheeler's test. He stared in silence. 60 degrees cooler. Sustained full-power operation. No sign of heat stress. The evidence was undeniable. The major knew it. Still, the idea of a plumber solving what 50 engineers couldn't was almost insulting to the military establishment. Tony's explanation was simple, almost painfully so. "Air behaves like water," he said. "If it won't flow where you want it, you give it an easier path. That's all this is, a bypass. The air goes directly to the cylinders that need it instead of wandering and overheating them." Peterson, unconvinced but intrigued, decided the test had to be confirmed. A second engine run was scheduled. The mechanics prepared Tony's modified engine for a longer and more rigorous trial. The plane's gauges, thermocouples, and instrumentation were checked. Engineers were present, skeptical of every reading. Yet when the engine was throttled to full power, the same results appeared. Rear cylinders held steady at around 430 degrees, well below dangerous thresholds. The crew couldn't believe it. Despite the evidence, the engineers were not impressed. Wright Aeronautical's chief engineer, Dr. Harrison Evans, immediately criticized the approach. The ducts, he argued, created turbulence, reduced total airflow, and violated fundamental aerodynamic principles. They were hand-fabricated, crude, and potentially fragile under long-term stress. "Yes," Tony replied, "but they work. The rear cylinders don't overheat. That's the problem, isn't it?" The engineers muttered among themselves. Calculations, simulations, and months of testing could not explain it. Tony didn't have a degree or lab reports. He had pipes, ducting, and the simple logic of fluid flow. And yet, every test confirmed the same thing. The rear cylinders were running safely at full power. At that moment, Colonel Curtis E. LeMay entered the room. LeMay, known for his aggressive leadership and disdain for excuses, had been overseeing the B-29 program in the Pacific. He had seen the losses, heard the complaints from crews, and was desperate for a solution. He listened silently as the engineers debated, then turned his gaze to Tony. "Sergeant," LeMay said, his voice low but commanding, "I have crews refusing to fly B-29s because the engines catch fire. You're telling me a plumber has fixed the problem with some aluminum tubes?" "Yes, sir," Tony said, nodding. LeMay's eyes scanned the engineers. "You've been working on this for 20 months. Did you get anywhere?" There was a long silence. No one could answer. The modifications so far had been marginal at best. Incremental improvements had failed to solve the core issue: rear cylinder overheating. Tony, a mechanic with no formal aeronautical training, had reduced the temperature by 60 degrees overnight. LeMay leaned back, exhaling through his cigar. "All right. Here's what's going to happen. You engineers will take this idea. You'll do stress tests, vibration analysis, material studies, everything necessary. But get it implemented immediately. Not in months. Not in weeks. In 20 days. Sergeant Valader will remain here to guide you. Do not overcomplicate it. If it works in the hangar, it can work everywhere." The room was stunned. The military hierarchy, the academic credentials, the wind tunnels, all bowed to the logic of a plumber who understood flow. Tony, quiet and unassuming, nodded and set to work with the engineers to explain exactly how the air bypass system functioned. Within days, Wright engineers began reverse engineering Tony's aluminum ducts, testing multiple configurations, measuring airflow, and verifying thermocouple data at dozens of points. The original idea proved surprisingly resilient. No other arrangement cooled the rear cylinders as effectively as Tony's original concept. What had seemed like a crude, makeshift modification turned out to be an elegant solution. A simple, reliable way to channel airflow directly where it was needed most. The first formal test was brutal. Engines ran at full power for 2 hours, far longer than any combat mission would require. The rear cylinders stayed cool, exhaust valves remained intact, and the engine survived conditions that had previously guaranteed catastrophic failure. For the first time, the B-29 appeared to have a reliable power plant, capable of completing long-range bombing missions without fear of spontaneous fire. By mid-October, the evidence was undeniable. Tony Valader, a plumber with grease-stained hands, had solved a problem that the world's top engineers had deemed impossible. The stage was set for the rapid implementation of his idea, saving countless aircraft, crews, and potentially the success of the Pacific bombing campaign. Once Tony Valader's bypass duct concept proved effective, the next challenge was translating a hand-built prototype into a production-ready solution. The crude aluminum tubes, cobbled together in a dusty hangar, were effective but not suitable for thousands of aircraft. Engineers at Wright Aeronautical and Boeing faced the daunting task of turning Tony's improvisation into standardized components that could be manufactured consistently, withstand vibrations, heat, and stress, and fit precisely into every B-29 engine produced. The engineers began by carefully measuring Tony's ducts, examining his sketches and running detailed airflow simulations. Every bend, every junction, every inch of the ducting was scrutinized. They conducted vibration and fatigue tests to ensure the aluminum wouldn't crack under the constant rumble of a 2,200 horsepower engine. Tony was consulted at every step, explaining the principle behind the bypass. It wasn't about moving more air, it was about directing airflow efficiently to the rear cylinders. The engineers, initially skeptical, soon realized that no amount of redesign could surpass the effectiveness of Tony's simple concept. Within weeks, technical drawings were finalized. The components could be produced using standard sheet metal processes. Every B-29 engine from that point forward could include the new ducts, now affectionately nicknamed Tony Ducts by maintenance crews. Retrofitting older aircraft already in the field posed a logistical challenge. Entire maintenance teams were mobilized, working around the clock to install the ducts on the B-29 stationed across the Pacific. Production lines were adjusted to incorporate the modification on new aircraft, and procurement teams rushed to source the aluminum tubing in bulk. The urgency was unprecedented, as every delay meant more aircraft lost to engine fires. By late November 1944, the first modified B-29s were ready for deployment. Among them was the bomber piloted by Captain Robert Fitzgerald, assigned to the historic city of Los Angeles mission targeting the Musashina aircraft plant near Tokyo. The 3,000-mile round trip would push the engines to sustained high power for nearly 9 hours, a severe test for any cooling system. Fitzgerald's flight engineer, Technical Sergeant Mike Romano, was acutely aware of the plane's history. He had tracked previous engine fires in his log and knew the warning signs. As the aircraft climbed to cruising altitude, the crew monitored the gauges obsessively, prepared for disaster. 2 hours into the mission, Romano noticed the rear cylinder temperature on engine number 3. The gauge read 438 degrees, well below the critical range. He double-checked the reading, tapping the glass, verifying circuit connections and comparing it to the other engines. Everything confirmed the same astonishing truth. The engine was performing perfectly. Captain Fitzgerald, expecting a fire warning any moment, finally allowed himself to relax. The B-29 had survived the flight without overheating, validating Tony's modification under actual combat conditions. Upon return to base, the ground crew inspected the engines. The cooling fins on the rear cylinders showed no signs of scorching or stress discoloration. Tony's ducts had performed exactly as designed. Over the following weeks, more B-29s equipped with Tony ducts completed missions over Japan, each one providing additional data confirming the reduction in rear cylinder temperatures. Pre-modification, the aircraft experienced roughly 4.2 engine fires per 100 flight hours. Post-modification, that number dropped to 0.7, a staggering 83% reduction. The operational impact was profound. Before the modification, the 20th Air Force was losing about 22 aircraft per month to engine fires alone. With Tony ducts installed, that number fell to just 4 per month. Lives were saved. Thousands of crew members who might have otherwise perished in midair explosions now returned safely from bombing runs. Strategically, the Pacific campaign gained momentum. B-29s could fly longer missions, carry heavier payloads, and maintain sustained bombing operations without the constant threat of losing planes to mechanical failures. The success of the modification also had psychological effects. Pilots who had previously feared their own engines began to regain confidence. Morale improved across the fleet. Crews now trusted that if their engines were pushed to the limit, the aircraft would hold together. For commanders like Colonel Curtis LeMay, the results meant more than statistics. They meant the ability to execute large-scale strategic missions that would directly influence the course of the war. Back in Dayton and Kansas, the engineers continued refining the design. Even though Tony's original hand-formed ducts were effective, the production-ready version underwent rigorous testing to ensure durability, vibration resistance, and thermal stability over thousands of flight hours. Every new B-29, whether rolling off the production line or retrofitted in the field, incorporated the Tony ducts as a standard feature. The seemingly small adjustment, some aluminum tubes redirecting airflow, had transformed one of the deadliest aircraft into a reliable war machine. By March 1945, over 2,100 B-29s had been retrofitted with the cooling ducts. Each aircraft now had a dramatically reduced risk of engine fire, ensuring that crews could fly long-range missions with unprecedented reliability. Tony Valader, a quiet plumber from Cleveland, had fundamentally changed aerial warfare, not through academic theory or advanced engineering, but through practical experience, intuition, and understanding how fluids flow. His solution didn't just save engines. It saved lives and altered the strategic landscape of the Pacific theater. By early 1945, the B-29 campaign over Japan had transformed. What had once been a nightmare of mechanical failures, burning engines, and terrified crews was now a well-oiled operation, thanks to a simple idea conceived by a plumber from Cleveland. The Tony ducts were in place across the Pacific theater, and the statistics told a remarkable story. Engine fires, which had once destroyed more planes than Japanese fighters, had dropped by more than 80%. What had seemed an unsolvable engineering problem now had a straightforward, reliable solution. The impact was not just mechanical, it was deeply human. Each B-29 carried 11 crew members. Every aircraft saved meant lives preserved. Over the final 12 months of the war, with Tony ducts installed in thousands of bombers, approximately 216 aircraft were spared destruction by engine fires. That translated into 2,376 men returning home safely, crews who could continue missions, complete campaigns, and ultimately contribute to the strategic pressure on Japan that shortened the war. Without Tony's modification, these numbers could have been drastically different. Each flight carried the risk of catastrophe. Now crews flew with confidence. The strategic consequences were enormous. With reliable engines, the United States could sustain a sustained bombing campaign deep into Japanese territory. Cities like Tokyo, Nagoya, and Osaka faced relentless aerial bombardment. The B-29's ability to reach targets thousands of miles away without fear of engine failure allowed for longer missions, larger payloads, and coordinated attacks that crippled industrial and military infrastructure. The Japanese military, long aware of the technical challenges facing the Americans, was forced to adjust its expectations. Captured Japanese documents later revealed the extent of their alarm. Lieutenant General Torosiro Kawabe, a senior Japanese officer, wrote in his diary that in the autumn of 1944, Japanese intelligence had assumed the B-29 program was failing. Their engines were unreliable, he noted. Our analysis indicated that losses would continue at high rates. We calculated that the Americans could not sustain operations over long distances. The B-29 seemed vulnerable and limited, until December 1944 when everything changed. Suddenly the Americans were arriving in greater numbers. Missions were longer, engines no longer failed midair, and the bombing campaigns intensified. Kawabe's assessment captured the shock and realization. We understood that we had lost the air war. Our calculations had been based on outdated assumptions about aircraft reliability. The Americans had found a solution we did not anticipate. The solution was invisible to them, a modest set of aluminum ducts, simple in design but powerful in effect. The human dimension of this engineering breakthrough cannot be overstated. Pilots who had previously refused missions were now flying multiple sorties with confidence. Flight engineers no longer spent every minute monitoring temperature gauges for signs of imminent disaster. Ground crews were relieved, knowing that engines would survive extended high-power operations. Lives, once at constant risk, were now protected by a modification that was elegant in its simplicity yet profound in its consequences. This breakthrough also reshaped the psychology of the war. Confidence in aircraft reliability allowed the 20th Air Force to plan complex, long-range missions that had previously seemed impossible. Without the threat of catastrophic engine fires, commanders could focus on strategy rather than crisis management. The momentum shifted decisively in favor of the Allies. Each mission flown without engine failure reinforced trust in the B-29 fleet, allowing for more audacious operations that directly contributed to Japan's eventual surrender. Meanwhile, back in Dayton and Kansas, the engineers continued refining the ducts, ensuring consistency in manufacturing and installation. Each aircraft that rolled off the production line now included the standard Tony duct system, creating a uniform standard of safety across the fleet. Retrofits continued on existing aircraft in the field, and maintenance crews quickly became familiar with the new design. Pilots and engineers alike adopted the nickname Tony Ducts, a quiet acknowledgement of the man whose ingenuity had saved both machines and lives. Yet despite the extraordinary impact, Tony Valader himself remained remarkably unassuming. He did not seek medals, fame, or recognition. He stayed in the hangars answering questions, guiding installation, and ensuring the work was done correctly. To him, it was just another problem to solve, another flow to redirect. The lives saved, the aircraft preserved, the strategic advantage gained, these were outcomes he never claimed as personal achievements. He was, in his own words, simply doing the job of a mechanic. By March 1945, the effectiveness of Tony's solution was undeniable. The B-29 campaign was no longer constrained by mechanical limitations. Hundreds of aircraft flew long-range bombing missions with minimal risk of engine failure. Lives were saved in astonishing numbers, the bombing campaign accelerated, and the Allies gained a decisive edge in the Pacific. What had started as a desperate crisis, aircraft designed to dominate the skies but threatening their own crews, had been transformed into one of the most reliable and deadly bombing forces in history. In the end, the story of Tony Valader and his cooling ducts illustrates a profound truth. Innovation is not always born from advanced degrees, wind tunnels, or years of theoretical study. Sometimes, it comes from practical knowledge, observation, and the ability to see a simple solution where others see complexity. A plumber's intuition, honed over decades of guiding water through stubborn pipes, had saved thousands of lives and altered the course of a global conflict. By mid-1945, the war in Europe had ended, and the Pacific theater was nearing its conclusion. The B-29 program had proven decisive, its fleet now operating reliably across vast distances. Yet in the midst of this monumental achievement, Tony Valader quietly prepared to leave the military. The man who had saved thousands of lives, a plumber by trade and mechanic by circumstance, had never sought recognition. He had fulfilled his duty, ensured the success of the missions and protected countless aircrews. But medals, accolades, and public acknowledgement were not on his agenda. Tony's discharge process at Wright Field in Dayton, Ohio, was routine, yet tinged with irony. Officers, engineers, and superiors all knew of his critical contribution. Suggestions were made that he receive the Army Commendation Medal for technical innovation. His response was characteristically simple. He declined. "I didn't do anything special," he said. "I just fixed a cooling problem. That's what mechanics do." To him, the lives saved were not a reflection of personal heroism but of practical problem-solving. He deferred any credit to the crews who flew the aircraft, the engineers who refined his work, and the countless men who maintained the planes in the field. Returning to Cleveland, Tony resumed his civilian life as a plumber. He went back to installing pipes, fixing leaks, and running water lines through stubborn basements and frozen homes. The B-29 program, the massive missions over Japan, the lives saved, these were not stories he shared with clients, friends, or family. His work at Pratt Army Airfield remained a private accomplishment, hidden behind grease-stained hands and modesty. Tony never sought fame and fame never found him. Yet the impact of his work endured far beyond his immediate circle. The bypass duct principle, which he had applied in its simplest form to the R-3350 engines, became a foundation for modern aircraft engine cooling. In the decades following the war, aircraft designers adapted the concept for new generations of engines. Directing airflow to areas that needed it most, creating low-resistance paths for heat dissipation, and optimizing duct geometry all trace their roots to the same insight Tony had in a Kansas hangar. Flow takes the path of least resistance, and if you want it somewhere else, you guide it. Modern engines, from the Pratt & Whitney F-135 powering the F-35 fighter to the General Electric G9X on the Boeing 777X, incorporate sophisticated versions of this principle. Engineers use advanced materials, computer-aided simulations, and precision manufacturing, but the fundamental concept, directed airflow to prevent overheating, is the same as the one Tony had improvised with sheet metal screws and scrap aluminum tubing. His quiet ingenuity echoes through the engines of modern aviation, a reminder that practical experience can sometimes rival the most advanced technology. Tony lived a long life, passing away in 1982 at the age of 76. At his funeral, few knew the full extent of his contribution to the war. Among the mourners, however, was a man who had flown B-29s in the Pacific. Now in his 60s, the veteran approached Tony's son after the service. "I flew 35 missions," he said quietly. "My crew came home because our engines didn't catch fire. I never met your father, but I spent 40 years trying to find the mechanic who built those ducts. I just wanted to say thank you." Tony's son, unaware of his father's wartime heroics, listened in disbelief. His father had never spoken of it. He had simply done his job. In the public record, Tony Valader remained almost entirely invisible. A brief newspaper article in Cleveland hinted at the story, but it received little attention. The world celebrated pilots, generals, and engineers, while the man who solved a crisis threatening thousands of aircraft went largely unrecognized. Yet for those who knew the story, the crews who flew the B-29s, the engineers who implemented his design, and the Air Force officers who witnessed the results, Tony's contribution was monumental. Without his cooling ducts, countless missions might have failed, thousands of lives could have been lost, and the strategic bombing campaign over Japan might have faltered. Ultimately, Tony Valader's story is a testament to the power of practical knowledge, intuition, and humility. A plumber, accustomed to solving problems in basements and apartments, applied the same logic to the deadliest aircraft engine of World War II. He did not invent new science. He simply understood how flow worked, recognized the problem, and created a simple, effective solution. In doing so, he saved lives, advanced aviation technology, and left a legacy that continues to influence aircraft design decades later. His life reminds us that innovation does not always come from those with titles, diplomas, or laboratories. Sometimes it comes from someone willing to observe carefully, think practically, and act decisively. Tony Valader, a plumber with grease-stained hands and an unassuming demeanor, changed the course of history, not with a bomb, a weapon, or a strategy, but with a few aluminum ducts, the right insight, and the courage to act. The B-29s flew further, longer, and safer because he understood one fundamental truth. When something won't flow where it's needed, you don't force it, you create a better path. In the end, his story is not one of medals or recognition. It is a story of quiet brilliance, practical innovation, and the lives saved by someone who never sought glory. The skies over the Pacific were safer not because of complex calculations alone, but because a plumber understood a simple, universal principle. And in that quiet understanding, Tony Valader became one of the unsung heroes of World War II. Decades passed after the end of World War II, and Tony Valader quietly returned to his life in Cleveland. The war was over, the B-29 campaign had achieved its strategic objectives, and the atomic bomb had brought Japan to surrender. For most people, the name Tony Valader was unknown. Newspapers barely mentioned him. Historians focused on generals, engineers, and pilots. Yet in the world of aviation, his influence endured. The simple principle that Tony had applied, directing airflow where it was needed most, became a cornerstone of aircraft engine design. Modern radial engines, jet turbines, and even the most advanced fighter jets incorporated the idea of guided cooling paths, airflow management, and temperature control. Engineers relied on simulations, computational fluid dynamics, and advanced materials, but the fundamental concept remained unchanged. Solve overheating problems by providing a clear, efficient path for the flow. Every engine that successfully operated at full power without failure carried echoes of Tony's ingenuity. Throughout the Cold War and into the 21st century, Tony's idea influenced aircraft ranging from the massive Boeing 777X commercial airliner to the stealth fighter F-35. Every engine with directed airflow owes a debt to the Cleveland plumber who had never flown a plane, never held a formal engineering degree, and yet had understood a problem that had confounded the best minds in America. Tony had seen the R-3350 engines not as abstract designs but as flow systems, much like the water pipes he had installed in basements for decades. The simplicity of his insight, the recognition that fluid follows the path of least resistance, revolutionized aircraft reliability. Despite this, Tony remained remarkably humble. He never sought fame or public recognition. He continued to work as a plumber, visiting homes, installing sinks, fixing toilets, and repairing heating systems. His clients never knew that the man who had saved thousands of lives had once been a silent savior of the skies. To Tony, innovation was not about glory, it was about solving a problem, doing a job well, and ensuring the safety of others. He often refused interviews and declined offers to speak about his wartime contributions. "I just installed some pipes," he would say. "That's all there is to it." Yet his impact could not remain hidden. Veterans who had flown B-29 missions over Japan remembered the aircraft's reliability, the confidence it gave crews, and the lives saved. One former pilot, decades later, sought out Tony's family to express gratitude. "I never met your father," he said to Tony's son, "but I owe him my life. He kept our engines from catching fire. He kept my crew alive." These quiet acknowledgments reflected the truth. Tony's ingenuity had directly altered the course of the war, the survival of air crews, and the effectiveness of the B-29 campaign. The story of Tony Valader serves as a profound reminder of how innovation often comes from unexpected places. It challenges assumptions about expertise, illustrating that deep practical knowledge, observation, and creativity can rival even the most rigorous academic training. Engineers in labs with wind tunnels, formulas, and simulations were stymied by the R-3350's overheating problem. A plumber, applying principles of flow and bypass, solved it in a single night. His approach was not flashy or glamorous. It was rooted in logic, intuition, and practical experience. Today, aviation continues to benefit from Tony's insights. Modern engines are monitored with advanced sensors, materials are engineered for heat resistance, and airflow is carefully directed to prevent catastrophic failures. Computational modeling, digital twins, and sophisticated diagnostics have expanded on his basic idea, but the guiding principle remains: air, or any fluid, flows naturally along the path of least resistance. If a critical system requires it to go elsewhere, one must create a better path. Tony Valader understood this in a hangar in Kansas long before modern technology existed to validate his approach. In reflecting on his life, one sees a profound lesson about humility, ingenuity, and service. Tony did not seek credit, yet his work saved over 2,300 lives and countless aircraft. He did not appear in history books, yet his contributions shaped the success of the United States air operations in the Pacific. He did not design for fame, but his idea became a foundational principle in aircraft engineering, proving that practical solutions can be as powerful as theoretical ones. The B-29, once a flying funeral plagued by self-igniting engines, became a reliable instrument of war because of his intervention. The atomic bomb missions to Hiroshima and Nagasaki, the firebombing campaigns, and the sustained aerial assaults over Japan all relied, in part, on the mechanical reliability that Tony had made possible. Every bomber that returned safely owed its survival to a simple modification conceived by someone outside the formal circles of expertise. Tony Valader passed away in 1982, leaving behind a quiet legacy that few recognized at the time. Yet for those who understand the story, he stands as an enduring example of how creativity, observation, and practical thinking can solve the most intractable problems. His life is a tribute to the notion that expertise is not defined solely by degrees or titles but by the ability to see, understand, and act effectively. He created solutions, saved lives, and changed the course of history, all while remaining true to himself and his trade. And so, the legacy of Tony Valader lives on in every engine that operates reliably under extreme conditions, in every pilot who flies safely, and in every modern aircraft that directs airflow efficiently to prevent overheating. The plumber who once crawled through Cleveland basements had, with aluminum ducts and insight, reshaped the skies of war and the future of aviation forever.